All right, here's our next lesson on exponential functions. So I'm going to go through this first part pretty quickly, so we have a little time on the later part. But here's the main idea. So an exponential function is one that's going to look similar to this. So some number times another number raised to a power. And here's the key. The exponent is going to be our variable. That's going to be our x in our problem. So a quick comparison of exponential functions and linear functions. So linear are what we're used to. Our y equals mx plus b. Equations that form a line. So y equals 3x minus 4, something like that. When we graph them, they're going to be straight lines. So we know about their slope, we know about everything else, but it's always going to be in a straight line. It's kind of increasing or decreasing at a steady rate. An exponential function is going to look more like this. So y equals 2 times 3 to the x, or y equals negative 4 times 1/2 to the x power. When we graph those, and as we'll see, they're going to be curved lines. So it might look something like this. So it's not increasing at the same rate, or sometimes it might be headed in the opposite direction, or it's not decreasing at the same rate, it's changing. So it's either bigger changes at each x or smaller amounts each x, rather than the same consistent amount each time. So in a table, it's going to look something like this. So maybe we have y equals 3 to the x power. So if I plug in a negative 2, it's going to get plugged in for my exponent. So that's 3 to the negative 2 power, which is really 1 over 3 to the second power, which is really just 1/9. Or 3 to the negative first power. So 1 over 3 to the first power, or 1/3. 3 to the 0 power is always 1. 3 to the first power is 3. 3 to the second power is 9. But you notice each time we were multiplying times 3. It was growing 3 times as big each time. Whereas with a linear equation, 2x plus 1. So 2 times negative 2 is negative 4, plus 1 is negative 3. Or 2 times negative 1 is negative 2, plus 1 is negative 1. Or 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus 1 is 3. Or 2 times 2 is 4, plus 1 is 5. This time they were increasing by 2, but adding 2 each time. So a linear equation increases at the same steady rate, just adding or subtracting the same amount each time. A exponential function is going to use multiplication to grow. So notice that this one, it went from a 1 to a 3 to a 9. So it went up by 2, then it went up by 7. So it's growing at bigger and bigger amounts as it goes. So here are what we look for, depending on the form that it's in. For exponential growth, a graph is a curved line. It's growing at a changing rate. So it's either increasing greater and greater or decreasing. The change is by multiplying or dividing by the same amount. And the variable is the exponent in the equation. For linear growth, our graph is a straight line. And the change is by adding or subtracting the same amount. So you may need to pause for a second, kind of fill that in, and then we'll go on with the next part. All right, so now we're going to look at some different examples and identify which is which. All right, so for the next one, these ones are pretty straightforward. That one is clearly a straight line. So it is a linear equation. The next one is a curved line. So it is exponential. You'll see it's growing by larger and larger amounts each time it goes up. All right. In a table, we want to look at how are the numbers changing. Are they being multiplied by the same number, or are they being added by the same number? So here, I went down by 3, I went down by another 3, went down by another 3. So this is going to be a linear equation. The reason is going to be it's changing by subtracting 3 each time. So we're using subtracting to change it. For the next one, I went from 0.25 to 0.5. Well, that's times 2. Then 0.5 to 1 is times 2. 1 to 2 is times 2. 1 to 4 is times 2. This is going to be an exponential function because they're multiplying by 2 each time. Okay, sorry for my handwriting there. So we're looking at, are they growing by the same steady amount, or are they multiplying, which means it's getting bigger and bigger and bigger and bigger each time. Now we got some word problems here. So it says Lola likes chocolate but claims it causes her acne. She chose to limit herself to 3 pieces of chocolate every 5 days. So every 5 days, it goes up 3 pieces. That's a linear equation. It's growing by a steady amount. Okay? So each day it's growing by the same 3 each time, so it's a nice steady line as it were to climb. Next one, Jordan decides to add running to his exercise routine and runs a total of 1 mile his first week. He plans to double the number of miles he runs each week. So this time, every week he's going to double it. He's going to multiply by 2. So the first week was 1, then it's going to be 2, then it's going to be 4, then it's going to be 8, then it's going to be 16. So this is an exponential function because he's multiplying by 2 each time. So each time it's going to grow by a larger and larger amount as we continue to multiply by 2. All right, so let's see that in some problems now. So here's the goal of our exponential functions. So something times another number raised to the power. So the x is what's going to be changing. How many times has that number been used over and over again? Sometimes we'll have an a, sometimes that a can just be a 1, and it's just b to the x power. So for each of these, we want to kind of write a function to represent what's going on and decide if it's going to be linear or exponential. So since Netflix has changed the video rental industry, more and more people are renting movies from them. When Netflix first started, 500 people became members. Each week, the number of members increased by 100. So we had 500, and then each week it increased by 100 for each of the weeks. So 100 times however many weeks is equal to my total amount. That makes it a linear equation because it's going on by an equal 100 each time. Next one. Each year, the local country club sponsors a tennis tournament. Play starts with 128 participants. During each round, half of the players are eliminated. So here's what my function is going to look like. I had 128, but each time I'm going to multiply it times 1/2 to see how many are left. So times 1/2 to the x power. So for every round, it's going to be another 1/2 that's being multiplied as I work my way down. So you can think of here as we're kind of dividing by 2, or we're multiplying times 1/2 each time, which makes it an exponential function. So it says how many players remain after 5 rounds. So we're going to plug in 5 for x. So 128 times 1/2 to the 5th power. And this is just where your calculator comes in for you. So 128 times 1/2 to the 5th gives me 4 players left over. All right, next two. A new strain of I think it was supposed to be otitis has begun to infect the world population. 10 people are infected on the first day the disease is contracted. Every day there are 5 times as many people with the disease. So our function is going to be y is equal to the starting amount 10 times 5 to the x power. Because every day it's going to be times 5, and then another times 5, and another. So it's going to grow bigger and bigger and bigger. So that makes it an exponential function. We want to know how many would be after 6 days. So 10 times 5 to the 6th that would give me a whopping 156,250 people would have the disease after just 6 days. Think about that, going from 10 to 150,000 in that short amount of time. All right, D, a science experience involves periodically measuring the number of mold cells represented or present on a piece of bread. At the start of the experiment, there are 50 mold cells. Each time a periodic observation is made, the number of mold cells triples. For an example, at observation 1, there were 150 mold cells. So our function is going to be 150. 50 is my starting amount. Each time it triples. That means we're multiplying times 3, but it's going to multiply by 3 over and over and over and over again, which is 3 to the x power. That makes this an exponential function. So when we see that we're going to keep multiplying by that same number over and over again, that's where we want to use an exponential function. All right, now let's put this to use and kind of tie in some things from earlier in the year. So here we're going to graph the function y is equal to 3 to the x power. So I already did a table of values for us, and I plotted the points for us here. Okay. What we want to identify are some key pieces of information from it. So my y-intercept, where does it cross the y-axis? Well, it crosses the point 0, 1. So my y, where y is equal to 1. My domain, remember that's my inputs, my x values. That's going to be x such that x is all real numbers. So think about it. There's nothing that I can't put in for that exponent. I can do 3 to literally any power that I would like. My range, though, is a little bit different. Do you notice how as I go to the right, it's going to keep increasing. So it's going to go on and on and on all the way up to infinity. But as it comes down, notice how it's getting closer and closer and closer and closer and closer to 0. But is 3 to any power actually going to give me 0? No. I can get a really, really tiny decimal. I can get into the negatives, but I'm never going to have not into the negatives. I'm going to get tiny and tiny and tiny, but it's never actually going to turn into a negative number or into 0. So my y's are y such that y is greater than 0. I can never hit 0. I can never drop below 0. I can never do 3 to some power and get a negative number or get a 0 number. Okay, but I can get smaller and smaller decimals and get closer and closer to 0. All right, so last two. If you think you got these down, go ahead and give them a try. If not, do them along with me. So here I want to do 0.3 to the x power. So I do 0.3 to the negative 2 power. Oh, sorry, I mistyped it there. And I get 11.11. And then I get 3.33. So at negative 2, notice down here I'm counting by ones down here. But on my y-axis I'm counting by 2s. Notice that notation there for you. So at negative 2, I'm up at 11. At negative 1, I'm down at 3.3. Remember, anything to the 0 power is just equal to 1. And then 0.3 to the first power is just going to be 0.3. 0.3 to the second power is going to be 0.09. And I'm just plugging that into my calculator. So I'm going to hit, sorry, I forgot my scale is 2. So 1 is going to be there. And then 0.3 is going to be here. 0.9 is going to be, 0.09 is going to be even closer to 0. So as I were to draw this line, it's going to look something like this. It's going to keep going on and on, closer and closer to 0 as I go out. And it's kind of decreasing over time. My y-intercept is 1, so 0, 1. My domain, that's my x values, I can plug in anything. So x such that x is all real numbers. And my range is, notice my y's can keep going up as long as I want, but they can't get below 0. So it's going to be y such that y is greater than 0. All right, next one. So 1/3 to the x power. So 1/3 to the -2 power. But then I'm going to add an extra 1. Well, that's going to give me 10. That's going to give me 4. Okay. If I plug in 0 for my power, that gives me 1 plus 1 is 2. Then I have 1/3 to the first power, that's 1/3, plus 1 is 1 and 1/3, or 1.333 repeated. Or 1/3 to the second power, plus 1 is 1.11 repeated, or 1 and 1/9. Okay. So let's graph these. Notice on my y-axis again, they're counting by 2's. So at -2, I'm at 10. At -1, I'm at 4. At 0, I'm at 2, because I added that extra 1. At 1, I'm at 1 and 1/3, so a little above halfway. And then I've got 1.11, going to be right above there. So you'll notice that I'm going to come down closer and closer. I'm going to kind of decrease as I come down. But I'm never going to quite get to 1. I'm going to get closer and closer to 1 on the y-axis, but never actually hit it. Because I can never turn 1/3 x into 0, and I'm always adding that 1. So it's always going to be 1 plus that tiny little bit of a decimal as I keep going out. So my y-intercept is 0, 2. My domain is the same, x, such that x is all real numbers. And my y is such that y is greater than 1. So it's going to get closer and closer to 1, but it's never going to quite hit that number.